Okay, in this lecture we are going to look at a summary for point estimates and interval estimates for the different unknown population parameters. So first of all, we estimated three population parameters: the population mean mu, the population variance sigma squared, and the population proportion p. So let's first look at the population parameter mu. The point estimate for mu is x bar, the sample mean. And then to set up the confidence intervals, if you look at this first block here, the first block is the situation where my population variance sigma squared is known. So for the first situation, we sample from a normal population. My sigma squared is known. Then my test statistic is x bar minus mu divided by sigma over square root n, and it follows a standard normal distribution. So to set up a 95% confidence interval, I have x bar plus or minus 1.96, and this 1.96 I get from my normal tables because my test statistic follows the standard normal distribution, and then I multiply it with the standard error sigma over square root n. If you look at the second star under assumptions, if I do not sample from a normal population, but my sample size is large, then my test statistic looks the same as above, and it follows an approximate standard normal distribution because of the central limit theorem. And then my confidence interval also looks exactly the same as the one above. Now, if we look at the second section on the population mean mu, that is the situation when the population variance sigma squared is unknown. Now, for the first star, my test statistic is x bar minus mu, and then I divide by s over square root n. S, my sample standard deviation, because my population standard deviation sigma is unknown. And this statistic follows the t-distribution with n minus 1 degrees of freedom. So if we set up our confidence interval, you will see that my critical value now comes from the t-tables and not from the normal or the z-tables. And I multiply with s over square root n because I do not have sigma, the population standard deviation. Now, the second star is when I do not sample from a normal population, but my sample size n is large. Then my test statistic looks exactly the same as the previous one, but now it follows an approximate standard normal distribution. And therefore, when I set up my confidence interval, my critical value comes from the z tables and not from the t tables. Okay, then the second population parameter that we estimated was the population variance sigma squared. And we estimate this variance, population variance, with our sample variance s squared. Now, if my sample comes from a normal distribution, then my test statistic is n minus 1 s squared over sigma squared, and it follows the chi-square distribution with n minus 1 degrees of freedom. And here in the last column, we have the 95% confidence interval, and we get our critical values from the chi-square tables. And then the last parameter that we estimated was the population proportion. Now, when we work with a large sample and np hat and n1 minus p hat are greater than 5, then our test statistic p hat minus p divided by the standard error follows an approximate standard normal distribution. And then we have the confidence interval in the last column. And you can see again, because my test statistic follows the standard normal distribution, my critical value in my confidence interval comes from the standard normal tables.